Good morning. Am I audible to you?
Yes, sir.
Perfect. So before we start, any questions so far? Any questions, concerns, confusions, clarifications? Okay. Yeah, Madhulika, yes, go ahead. You wanted to say something? Okay, so before we start some what you call some organizational issues, so we all together we need to conduct 3 quizzes for the overall course. So one of course before minor one, okay, and two between minor one to majors with sufficient what you call time intervals. So Ashutosh, would you be able to coordinate and give me some give me some potential options so that I can freeze a few days? Hello, are you there, Ashutosh? Or Dev?
Sir, we will do that.
I really
I will tell
need
Ashutosh about that.
yeah. So what we really need is I guess your minor starts from 16. I think is that so?
Sir, 19th. 19th.
So we need to have one quiz conducted maybe at least 1 week before that. Then two between the time between the minor one after the minor one exam to the major. So we would take best out of those two. So please uh, help me to schedule this and
the class timings, or like would you call an extra
no
class?
no, so we don't need to use it in extra class. I think our tutorial timings and the doubt clearing timings are available and we could use that.
Fine, sir.
So we can have a quiz in next week, maybe
No, I am
Friday or
fine,
something.
but I think yeah, so I really don't want to fix, after fixing, I really don't want to change anything. So if you really need to take a poll among your group and tell me a date, that should be the best thing that I would suggest, and so that I would fix. So I am okay with any date and time. And of course it's going to be an online quiz, so I really and I don't want some exemption after that, so you can anytime next week or next week is good to me, and we could use 4 of our afternoon slots between 1 to 2 to do that, or any other time. We can keep our class timings intact so that it won't get disturbed. Is that fine?
Yes, sir. So, and would the quiz be for 1 hour?
No. It would be 30 to 40 minutes maximum.
Fine, sir.
So we'll continue the session. Okay. So what we were trying to do was to understand the dynamics of various systems. Okay. So we were trying to understand the dynamics of first order systems with respect to this, with respect to the various set of inputs. Similarly, So if you start looking at it, we were trying to see the first order system dynamics. For three major type of input. In fact, four major types of input that we were looking were step, okay, then RAM and pulse. Of course, we did not go into the detail of the pulse input, but pulse is a combination input of step, fine. Then we have the sinusoidal input. So we have seen the first part of that. What we have seen is how to calculate the transfer function of, not how to calculate it. We would be most likely using a ready-made transfer function model that we have already learned how to use it. And then we would we have seen step, and we have seen how the RAM transfer function looks like. Fine. Then a rectangular one, and of course a sinusoidal one. And so this is the input transfer function. So as we have seen, what we are really interested to get y of s. Y of s is what? Let's say your g of s is your transfer function times u of s, and u of s is what? Your input transfer function. So you will get, when you multiply them together by virtue of the properties of transfer function, you only need to multiply your transfer function, process transfer function with the input transfer function to get your output transfer function. Then if you get the, so see, we have to understand that this is all in the Laplace domain. Everything is in Laplace. We need to move to the time domain. Eventually, that is what we really understand. Laplace is a transform space, and you need to do Laplace inverse. So you would get your y of t. This is easier to understand. All the manipulations you would do in the Laplace space, and you convert them to the, and to do both of this, what is our what we really, you just need to use our Laplace table. So coming back to the, so we have seen how a step input transfer function looks like. Then we have seen how did we calculate the output transfer function. Then we will take the inverse y of t to check to see what is the how output is varying with respect to time. And for the first order system, we see a peculiar response, which is which which is what we call as negative exponential behavior. So initially the response will be very fast, then it becomes sluggish, and finally it becomes converged. So this one means that this is the normalized output. So y is the output, y by km. So this is the maximum output that it can do. Finally it would reach the fine without offset. You see that it would eventually reach your target. And if you look at, if you plot the, so see the output expression as y of t is equal to k times m. M is the amplitude of your step, and k is the gain of your transfer function, 1 minus e raised to t by tau. So, and if you, so what we have plotted here is y by km. So, which is the normalized output, because why do we call it as normalized? When t tends to infinity, when t tends to infinity, that is like the final time that you could think of, y of t become approximately equal to km. So that is the maximum that an output can reach. So y by t is y of t by km is the normalized output. So it would, y of t by km can maximum go up to 1. And when we plot this response, y of t by km with respect to t by tau, which is the normalized time, okay, what you would really see that when t is equal to tau, And we can see V is equal to tau, T is equal to 2 tau, 3 tau, and so on and so forth. When T is equal to tau, the process has reached 63% of the overall output. Overall output, let's say it is 1. Your output Y by Km would reach 63.2%, which is, so this particular time, which is T is equal to tau, it is called time constant. This is a characteristic of first order system. If you have, if you see the response of the first order system, what you would really see is that after uh, time time equal to the time constant, one time constant, you would really see your output is equal to output has at least 63.2% of the overall process, and by approximately by 5 time constants you would tend to reach. So when T is equal to time tau, this would be approximately 63%. And when T is equal to approximately equal to 5 tau, 4 to 5 tau, you would really see that you're up, so you are close to 100%. Why I am saying close to? Uh, because 100% might not be able to achieve with some numerical fraction. So you would really see that 5 tau, it would reach 99.33. It is not fully 100%, but to some extent. So any questions so far? Okay. So now with the same logic, we started looking at the first order system with ramp input, and that was a bit more involved due to the fact that y of s you will have to write as partial fraction, because you don't have this particular standard form in the Laplace table, so you will have to do the Laplace write them in factorize into standard form. Then you will be able to see what is the inverse of each of these. And while doing so, what are you going to get is a is a term that contains an exponential term, okay, which I'll call it as 1, and a linear term, which I call it as 2. So what you would really see over the time when t is high, when I should not say infinity, when t is sufficiently large, this this particular term would this particular term, which this exponential term would tend close to 0, and what would be remaining is ka t minus ka tau, so which is ka t minus tau. So when you try to plot the output response, what you would really see that initially it would have this exponential characteristic. That's why it takes a turn here. But when t progresses, the effect of the exponential term would be diminishing as we see. Then it would be mostly, then afterwards the linear term would start to become dominant. So what we would really see is this then. And if you want to approximate this, you can you can try to draw a tangent and try to cut it over here. So it's like, so the real response would be so if you approximate when t is equal to tau, you see that when t is equal to tau, would this this line would cut your x tau, and the overall response would be till that time it would be exponential term would bring in some sort of non-linear dynamics. Okay, then afterwards it would be perfectly linear. So any questions so far? This was the last thing that we have discussed. Okay, so if we don't have, so any questions, please, if you have anything which you would like to discuss, let's discuss that before we move ahead. Okay, so the next is with the same spirit, we will look at the sinusoidal response. Okay, so the steps are not going to change, but only the mathematical nuances would keep on increasing. It's because the transfer function of the sinusoidal input is AW by S plus S square plus omega square, where W is the angular velocity, or like so. Sorry, not angular velocity, angular frequency. So what would eventually happen? So when we multiply them together, so you would get again y of s. So this is your transfer function, and this is our input. When we multiply them together, the expressions are become more clumsy in nature. And this essentially means that you will have to take again split them up according to partial fraction. So that part is omitted for the timing. Again, you could check for yourself. Because we will have to separate them as, okay, so there are three factors, right? So one is of course tau s plus 1. Huh? So let me do it. So the three factors that you would have to figure out would be one, let's say by A by tau s plus 1 plus Vs by s square plus omega square and C by s square plus omega square. So we have to calculate A, B, and C, which are these values. You can check it for yourself, and we have seen how to do it. So you can take a common factor out, then multiply with the corresponding term, substitute, eliminate one of the variable by substituting s is equal to 0, and so on and so forth. So you have learned how to calculate vertical fractions in. So once we do that, we will get three nice terms. So these three terms are in the standard form. So this is the first order term. This corresponding to the cosine, and this corresponding to again sine. So what would happen is, okay, when we take an inverse Laplace, okay, so this would be Wt times e raised to minus t by tau, as we all know. This would be omega tau, this would be cos omega tau, and this would be sin omega tau, omega t on tau though. And we know, so this is like, this forms like a sin omega t plus b cos omega t kind of a form. We'll be able to write them as sin omega t plus phi, okay, with such that this phi is equal to tan inverse b by a. And c, so which is c would be a square plus b square. So this is the standard form that we all know. Just a second. Sorry about that. So this is the simple trigonometric expression that we all know is sin omega t plus b sin omega b cos omega t becomes c sin omega t plus phi, while c stands for the uh, uh, square root of a square plus b square, while phi stands for tan inverse b by a. So in that way, your output becomes a very, very compact and what you call become very compact. One term contain an exponential term, other term contain a sin omega t term. Okay, so now let's try to plot this response qualitatively, and we have seen what would happen. So after some time, the exponential term tend to kind of contribute less, and mostly the sin omega t term is going to get contributed. So initial part you would have an exponential effect, and of course the effect of the sine term, and after some time this exponential term would decay and mostly the sine term would lead into the prominence. So these are so the aim here is just to give you an idea how to compute the response. So instead of having a sinusoidal response, okay, so let's say you are given with a new type of function. Still you should be able to calculate all of this. Only thing that you need to do, again, the overall expression is y of s is equal to g of s, which is the transfer function of the process times u of s. And if you know the u of s could be anything. We have seen some candidate functions which are step, ramp, and sine. But there could be anything. So it could be a sawtooth function, for instance. So in that case, you will have to apply the corresponding Laplace transform of y of s over here and multiply g of s and y of s and calculate the inverse. So the method is fairly same. Only thing you have to take a look at, the key aspect that you need to pay attention to, when you write the y of s expression, it has to be in the standard form. So you should be able to split this particular y of s into terms that contain, let's say, a, b, c, that contain all the standard form. So then only you will be able to compute the inverse Laplace, because your table contain only the standard forms. If it is, let's say, by some means, if you are got stuck with non-standard form, use partial fraction and convert them into standard form, take L inverse. So this is by and large the overall steps that you would focus. So any questions before we move to the second order system? Any confusions, any questions? Anything that is not clear? Your textbook contains few more examples. You will be able to take a look at that and practice. But I think eventually you should be able to do with any standard, any function, any input function that is given to you, because the procedure is pretty standard. Any questions? Anyone? Ashutosh, Aditya, hello.
Sir, I had gone somewhere in the first half of the meeting, so you were telling something about the poll that we have to conduct. Could you please tell me about that?
Okay, so see, we should be able to conduct 3 quizzes as part of this course. Okay, so out of which two would be considered for evaluation. So we need to have one conducted before minor one. Two would be between minor one and major. So what I would suggest is, if you could freeze those dates now, it would be the best.
Sure, sir. So when would I
So
tell
you can, pardon?
when should I tell you about that? Like when we have finalized it?
So you can tell me in couple of days time, 2-3 days time, because if you want to conduct an exam next week, I need to have some time.
Sure, sir. Sure.
So if it is, I would prefer if I get the date, let's say by Thursday.
Okay, sir. We'll try by this weekend. And on any preferable days that you would want it to be? Like,
I
would
know
you
I
want?
am perfectly fine. No, I am perfectly fine with any time.
Okay, sir. Like we'll try that it is conducted during the class hours so that it does not clash with any other.
It would be either class. So I would prefer Am I audible now?
Yes, sir, you're audible.
Give me.
So I was asking about the class schedule, sir. Could it be done in the class hours itself?
No, I'm fine with class hours, but we could, if we could do it in the 2 hours, that would be nice, so that we won't kill our class timings. But if there are no way out, we could even do it in the class hours. It's just 1 hour. It should be okay.
Sure, sir. So I'll look about it, whether tutorial hours or class hours, and one before the minor and two after the minors.
Yeah, absolutely. Perfect.
Okay, sir. And there was one more thing, sir, regarding this week's tutorial. You had asked us last
So
week that we
yeah,
had
so is Thursday is a good time for you?
Thursday 12 p.m. would be good, sir, because I don't think anyone
12
has.
noon.
Yeah,
12 or 1?
12 noon because we have classes till 12, so we can wind up the day by 1.
Is that so? Let me also look my calendar. I would have a अच्छा, just a 12 won't work. Uh, yeah, so maybe we can do between. So is this true for the biochemical guys too?
Yes, sir. Yes, sir. I talked to the biotech guy as well.
Okay, so let me talk to my TS. If they don't have any class, I think we shall do it on 12. Otherwise, we will do it on Saturday. Okay.
Okay, sir. I've talked to the class rep. Probably he's not here, but I've had a discussion with him, and he said that they have this slot free.
No, I'm fine with that. What I'm trying to say is, let me also check with the TA. So because they should also be available that time. No? If the timing is, if the timing is convenient to them also, then we will do it. Otherwise,
Sure.
some other day.
Yes, sir.
So just give me a minute. So let's restart our class. And okay, so coming to the, so see, so far we have seen first order system, which is the simplest thing that you could think of. Very simple. The simplest example of a first order system is a tank. Okay, there is a feed in, flow out. And let's say if you are trying to model the height, we have seen this. So let's say you're out at the height as a function of, I think, inlet flow rate. Yes. So this is the simplest example of a first order system. But most of the things that you would really see in practically, its order would be higher than the first order system. So we are also kind of motivated to learn higher order system. So we'll start with the second order system and we will see some peculiar examples of higher order system. So what is a second order system? So again, so first order system, the simplest example is, how do you check your system is first order? You have to just look at that transfer function and the denominator polynomial is first order. Fine. Similarly, for the second order system, again, the thumb rule should be the denominator polynomial should be second order. So tau square plus 2 theta. So we will talk about what is this zeta and all, but what we have to take a look at here is that it has to be a second degree polynomial in the denominator. And it's all the denominator. So we have learned this earlier. So anything that you characterize a transfer function, it should be only the denominator term, not the numerator term. the characteristics of the transfer function is mostly determined by the denominator system, at least the order and things like that. Okay, so this is a standard second order function, and they should also be a cascaded first order system, which means that if there are two first order systems somehow connected in series, that should be resulting in second order system. So we have seen an example last time. So let's say if you have, so this is a, so let's say this is a first order system. You are trying to model flow in and flow out, and eventually you are, so give me a minute from after the pencil chart for the start. So F in and F out. So we have seen this height when modeled as the function of inlet, it would eventually be a first order system. Okay, and the second order system could be either, so there are two reasons for what you call a system to behave like second order. First would be first order systems in series. Okay, and the second could be by virtue of the same. So what is second order, first order systems in series? So let's say you have two tanks. So this is quite common in process industry. Two tanks, and you have F1 in, and let's say F1 out, and which is really your and you have your F2 out. F1 out maybe is going inside as inlet to the tank 1, tank 2. So let's say if you would like to develop the height of tank 2, so basically this guy as a function of inlet 1. So here you have a first order dynamics. Here also you have a first order dynamics, and we have seen how transfer function interacts. If there are, and we have seen how, let's say this is the transfer function G1, and let's say this is the transfer function G2, and this is your output Y, and this is your input U. So it is happening the same way, no? So here, let's say a transfer function G1, here is a transfer function G2. The input is first going to the transfer function 1, then that is going to the transfer function 2, and finally the output. So we see that this G1 and G2 get multiplied together. So it is, you can write as a simplified transfer function G1 G2 times Y, and G1, let's say it is first order, and G2 also, let's say first order, and first order, two first order systems in series would multiply them together. For instance, let's say K1 by tau 1 S plus 1, okay, K2 by tau 2 S plus 1. Eventually what would happen, it would be K1 K2, if that's another constant. So we'll get tau 1 tau 2 S square, then tau 1 2 times tau 1 plus tau 2 times S plus 1. So you see that again this S square is coming into the picture here. So this is one.
Over there.
Pardon?
Why is it 2 over there?
Yeah. So there is no 2 here. So it is tau 1, tau 2 s plus 1. So eventually, what we are trying. So see what. So what are so this is kind of synthesized system. You have two systems connected by virtue of their interaction. It has become second order. And there are certain examples. For instance, you would see in the lab. For instance, YouTube manometer. So it's important that you connect these models with the physical system. So this is two tanks connected in series. So this is a physical system, two tanks, and the second is immaterial. So you have a YouTube manometer. Okay. In the YouTube manometer, what will you do? Let's say if you would like to figure out the response of the system with respect to time. So let's say you have a manometer here, and you filled in this with water. And let's say you have applied an air pressure here. So this is water. So and you apply an air pressure here. Just applied the pressure and taken off. And let's say this is, you have a reference here, and this is the meniscus, one meniscus. Let's say this is H. And what would happen? So your meniscus level would go up and down. Okay, and let's say you are trying to note this h of t as a function of time. And what you would eventually see that, so it would go up, eventually it would die out. This is time. This is h of t. So this is also a second order system. Why? So it's not very easy to understand why this has become second order, but when we try to model them, you see that, okay, it would contain the transfer function would be of this particular form, tau square s square, okay, then you will say 2 zeta tau s plus 1. We'll talk about what is this theta. So that is a key variable that controls the characteristics of it. So these are the two, what I would say. So in short, this is by virtue. So why this second order characteristics? This is by virtue of physics. And so this one is by virtue of augmentation. So initially, it had only the dynamics is just first order system, but you augmented to first order systems, and by the rule of by the Laplace transform rule, because two transfer functions are getting interacted to each other, and that becomes a second order system. So any questions so far? Before we move ahead. Okay, so now let's see some standard cases. So okay, so this is what I have tried to say. So it could be either due to the physics, so that you would see a second order dynamics, or it could be two first order systems connected in series, as in here. So now so see, if you look the second order dynamics with respect to the first order dynamics, so and try to kind of understand what are the additional thing that comes in here. We know what is the gain. So how do we define the gain? So we have seen that output change minus input change. So that would result in gain. So this is something that we have learned in the first order system. Something that's not new for us to understand. Tau, okay, we have learned about time constant, but the time constant in the second order system has a different meaning. It is not 63.2% of the overall process. That's only for first order system. But again, so we know this variable. We have seen it's called time constant. But the additional variable that comes over here is this theta, so which we have not seen in first order system. So what is that is now we have to take a look at it. So what are the additional things that governs the second order dynamics? So that's what I told. K and tau has the same importance or the same information. They brings in the same information. Because K is process gain, it is tau is the time constant. It would determines the speed of response, but speed of response is not exactly. So this speed of response is not exactly same as the first order system. Here the speed of response would be different, but the tau only governs the speed of response. So in the first order system, you have seen that at 5 time constant you are reaching the final value, and for 1 time constant it is 63.2%, and this is in between. Tau, I would say 1 tau to 5 tau. So this numbers would be different over here because this is second order system, but by and large tau only governs the overall speed. And the theta is the additional variable that we have not seen in the first order system. It's called damping coefficient. And it is dimensionless. Okay. While tau and k need not be dimensionless. It would have, so tau would have units related to time, while k would have y2 minus y1 by u2 minus u1. So your output and input units would play a role in defining the units of k, while time constant would have the unit of the time constant somewhere related to the overall time, while theta is a dimensionless quantity. And it's also called damping coefficient, damping factor. And why you are calling it as damping here? So generally, in the second order, in any second order system, unlike a first order system, the response won't be smooth. For instance, we have seen how the YouTube manometer, it's a response that we have seen. So it would be oscillating, and finally it becomes steady state. So there is, unlike the first order system, which here the response is smooth. It's because it just increases and settles at point, while the second order system, it could be oscillatory in nature. Need not be always oscillatory, but it could be oscillatory. And zeta is the term that governs the level of oscillation. So we would see that when the zeta value for a system is greater than 1, okay, then you call it as an overdamped system. We will see why it is so. And when theta is equal to 1, it is critically damped system. While theta becomes 0 to 1, it is called underdamped. So when a system is underdamped, that tend to be oscillating. And when become either critically damped or underdamped, critically damped is if it is a critically damped system, it comes somewhere in the middle of overdamped and underdamped. While in the overdamped case, the dynamics become very slow. So we'll call it a sluggish. So you would see all spectrum of responses. One is very sluggish, one would be highly oscillatory. Unlike in the first order system, there is only one type of response. Here you would see three different type of responses that basically characterized by the value of this zeta. So why, and we will see why why they have three different responses. This also has some connection with respect to the roots of the denominator polynomial. You see that when zeta is greater than 1, the roots of your denominator polynomial, which is this tau square s square plus 2 theta tau plus 1, would be real and unequal. While in the second case, it becomes real and equal. Okay, and the third, when it becomes 0 to 0 less than zeta less than 1, they become complex conjugate. So this complex conjugate character bringing the oscillation in the underdamped case, the real and unequal characteristic brings in the sluggishness into the overdamped case, and critically damped is somewhere in the between, and the roots would be real and equal. So if I want to draw, so this is oscillatory. I'll call it this as underdamped. Maybe let me try to draw it. So we would have three different cases. So let's say if I wanted to plot y of t with respect to t, okay, and let's say this is your target. Let's say I would say this is normalized y of t, and you could see there are three types of response. Okay, so this is underdamped, where zeta is less than 1, okay, and you would see that something critically damped, okay. This would be theta is equal to 1. This is critically damped. It is very close to first order system. So critically damped dynamics is what we see very close to first order. And the other one is overdamped, becomes very slow. Okay. Sometimes over. And your y of s is k by tau square s square plus 2 theta tau s plus 1. So this is your model, and these are the three potential options. And they are all dictated by, all these characteristics are dictated by the theta, which is a dimensionless value. So any questions at the moment? Any questions? So that's why this is called. Okay, so now what is this? So let's say how do you physically connect it? Okay, so let's say you have a you have developed a system, and for instance, the underdamped case might correspond to a case when, and with an automobile suspension system without ineffective shock absorber. So there is no so you are trying to model the what you call the dynamics of an automobile, and if let's say it has ineffective shock absorber, which means that your system tend to oscillate, correct? And so systems tend to oscillate. So that is essentially is a reflection of underdamped. So any questions so far? Any questions? Anything that is not clear? Any confusion? Okay, so I'll go ahead and probably yeah, a few more slides I'll cover and I'll take a pause. Okay, so if you have two first order systems connected in series, we have seen that that results in second order dynamics. Okay, so second order dynamics essentially means that, see, your Laplace and ODE. So you can come from ODE to Laplace and you can go from Laplace to ODE. So essentially second order system in the Laplace domain means that your ordinary differential equation that represent that dynamic is of second order. So if the ordinary differential equation was first order, you should have got a first order transfer function onto. So the name, so what I'm trying to say is whatever we are saying here in the Laplace, that is exactly same in the ODE space also. Or whatever is happening in the ODE space, the same thing happens in the Laplace space. So we are not bringing anything addition. If it is a second order ODE, so Laplace it would be second order polynomial. Okay. Of course, in the denominator. And if you see that if your transfer function is second order polynomial, in the ODE space it is a second order ODE. So this vertical has to be kind of cemented in your mind. So we are not bringing anything additional. So it is just a transformation that changes the property. In one case it is an ODE, in the other case it is a polynomial or algebraic equation. Okay. And what I am trying to say now, so let's say if you have an under second order system that is generated by or either generated by augmenting to first order, and that eventually the transfer function would be tau 1 tau 2 s square tau 1 plus tau 2 s plus 1. That is what it is written over here. While if it is naturally developed, which means that it is not connected, by virtue of its physics, it becomes second order. So as I told, this may be tanks in connectors, and this can be a U-tube manometer. And example, that is also a second order system where, so here, so if you want to kind of equate both of this, so this tau 1 square corresponding to tau 1 tau 2, so tau is root of tau 1 tau 2, zeta here would be corresponding to tau. So here you see that, so you can check it. So you will have to just equate and figure out. So the here 2 zeta tau is equal to basically 2 zeta tau is equal to tau 1 plus tau 2. While tau is square root of tau. So theta would be tau 1 plus tau 2 divided by 2 times square root of tau 1 tau 2. Okay, and what are the roots here? So basically you would have roots, right? So so you will have values of s that gives it. So you can figure it out. So minus b plus or minus, how do you calculate it? Minus b plus or minus roots b square minus 4ac by, so you know that equation. So you can write that and calculate how the roots of this denominator equation comes out. And again, to recall, if zeta greater than 1, it become overdamped, less than 1 become underdamped, and zeta is equal to 1 become critically damped. And just to add up, overdamped most likely, and okay, so how overdamped system originate? Most likely it would be systems connected in series or tanks. That can be overdam, underdam, mostly physics related. For instance, YouTube manometer, and if there is some air pressure related line flow, they are all resulting in underdam system. And if things are connected, then that would result in overdam system. And of course, critically dammed system comes in between. So you can change some properties of either underdammed and overdammed system and bring into critically dammed system. So critically dammed system does not originate as it is. You can, so it is like this: overdammed, underdammed. So here it is critically dammed. So you can come in here and make it critically dammed. You can come in here and make it critically dammed by changing some parameters. For instance, if you keep good shock absorbs in a system, this is the original automobile which was underdamped, which become critically dammed. So I'll stop here, and if you have some issues, we can discuss now or anytime whenever you are available. And if you have some problem in understanding anything, not getting any idea, some confusion, clarification, feel free to come to the doubt clearing session and discuss, or write an email to me, or write an email to our TAs, or anything would do. So make sure that you are clear in these things before we kind of go to the control aspect of it. Now we are just doing the dynamic. So make sure that these things are cemented in your mind. Anything that you would to add? Otherwise, it's already 11. Your classes would be going on, and we may be able to close the session. Anything that you want to add? All okay?
No, sir.
Okay then, guys. See you tomorrow, and please update me with the date, and bye bye for today.